The pump should have exploded. Everyone in the room knew it. Dr. Isaac Lubbock stood 3 meters from the examination table, staring at the object that had killed 2,654 British civilians. The object stared back, silent and intact. A German V-2 turbopump. Serial number B47331. Recovered from a rocket that struck Antwerp on March 27, 1945. The rocket traveled 310 kilometers in 63 seconds before impact. During those 63 seconds, this pump moved 125 kilograms of propellant per second into a combustion chamber burning at 2,700 degrees Celsius, 125 kilograms per second. Lubbock repeated the number silently. British rocket pumps failed at 12 kilograms per second. They failed violently. 3 engineers died at Westcott in June testing a pump designed for 18 kilograms per second. The explosion destroyed the test cell. Investigators found fragments of the pump housing embedded in concrete walls 40 meters away. The pump had operated for 8 seconds before catastrophic failure. This German pump ran for 63 seconds, without failure, without even visible damage. Lubbock walked closer. His hands were shaking slightly, not from fear, from something worse, professional inadequacy. He had worked in propulsion engineering since 1938, helped develop fuel systems for Rolls-Royce Merlin engines that powered Spitfires and Lancasters, understood pumps, turbines, combustion dynamics, thought he understood the limits of what was mechanically possible. This pump violated those limits. The turbopump assembly sat on the examination table under harsh electric light. Approximately 340 kilograms total mass. Cast aluminum housing, 680 millimeters long, 420 millimeters maximum diameter. 2 centrifugal pumps mounted side by side. Between them, a turbine wheel. The turbine spun at 3,800 revolutions per minute, driven by steam from decomposing hydrogen peroxide. At that rotational speed, the centrifugal forces trying to tear the turbine wheel apart exceeded 4,000 times gravity. The wheel held. The British metallurgist who examined it yesterday said the turbine blades were made from nickel-chromium superalloy, operating at 750 degrees Celsius. Britain used similar alloys in experimental jet engines. Those engines operated at lower temperatures, lower stress, carefully controlled conditions. Test runs lasted minutes, not continuous operation. The V-2 turbine ran continuously for over a minute under maximum load in combat conditions. One of the 2 pumps handled liquid oxygen at minus 183 degrees Celsius. The other handled ethanol fuel at ambient temperature. The temperature differential between the oxygen pump and the adjacent turbine was 933 degrees Celsius. They were mounted in the same aluminum housing separated by 80 millimeters. Lubbock had consulted with materials specialists at Imperial College. They said thermal stress from a 933-degree differential should crack aluminum castings catastrophically within seconds. The housing showed no cracks, no warping, no distortion. It looked like it came off a factory production line yesterday, not from a weapon that flew 80 kilometers altitude at 5 times the speed of sound before slamming into a Belgian city. Behind Lubbock, someone coughed. He turned. Wing Commander Gerald Ashford stood in the doorway holding a folder marked "Secret" in red letters. Ashford commanded the rocket propulsion department at the Royal Aircraft Establishment, former RAF pilot. Shot down over France in 1940, escaped through Spain, returned to England and transferred to experimental weapons development. Smart man, political man, dangerous combination. Ashford walked to the examination table, placed the folder down, looked at the turbo pump without expression. "Your preliminary assessment, Dr. Lubbock?" Lubbock chose his words carefully. "The engineering is exceptional, sir, significantly beyond current British capability." "How significantly?" 10 years, perhaps 15. Ashford's expression did not change, but his jaw tightened almost imperceptibly. 15 years. "At minimum, sir. The materials technology alone requires fundamental advances in metallurgy. The manufacturing precision requires new machine tools. The design philosophy is entirely different from British practice." "Explain the design philosophy." Lubbock pointed at the turbo pump. "British designs prioritize safety margins. We specify thicker materials, lower operating stresses, redundant systems. Conservative engineering. This pump has no safety margins. The housing is 12 millimeters thick aluminum alloy. British practice would specify 18 to 20 millimeters minimum. The turbine operates at material limits. The bearings run in liquid oxygen, which is violently reactive. One contamination particle, one manufacturing defect, one material impurity, and the entire assembly explodes. But it did not explode. No, sir. It did not explode because every component is manufactured to exact specifications using optimal materials. The Germans accepted zero margin for error. They compensated by achieving perfection in execution. Ashford picked up the folder, extracted a single sheet of paper, handed it to Lubbock. The paper was a memorandum from the Ministry of Supply dated September 10, 1945. Lubbock read quickly. His stomach tightened. The memorandum outlined British rocket development priorities for 1946 through 1950. Target: develop guided ballistic missile with 500-kilometer range, 1,000-kilogram warhead, operational by 1950. Required propulsion system: liquid fuel rocket engine generating 25,000 kilograms thrust. Required propellant flow rate: 120 kilograms per second. The numbers were nearly identical to V-2 specifications. Lubbock looked up. They want us to copy the V-2. They want operational missiles, Doctor. How we achieve that is our concern. Sir, with respect, we cannot simply copy this pump. British materials and manufacturing methods are inadequate. If we attempt direct replication using available resources, the pumps will fail, catastrophically. Ashford leaned against the examination table. The Soviets captured Peenemünde facility in May. Intelligence reports indicate they are dismantling the V-2 production equipment and shipping everything to Moscow. They also captured German rocket engineers, approximately 200 specialists who worked directly on V-2 development. The Americans captured Werner von Braun and his senior team, approximately 120 engineers, also captured complete V-2 technical documentation and 100 intact rockets. Britain captured this. He gestured at the turbopump. One functional example. Some incomplete technical drawings, no German engineers. We are already behind in a race most people do not yet realize has started. Lubbock felt the weight of the situation settle onto his shoulders. What are you asking me to do, sir? Disassemble this pump completely. Document every component, every material, every dimension, every design feature. Find out how it works and why it works. Then determine what Britain needs to build equivalent capability. That will take months of analysis. You have 6 weeks. The minister wants a comprehensive report by November 1st. Assessment of German technology, evaluation of British capabilities, recommendations for development program. 6 weeks. Lubbock looked at the turbopump. The aluminum housing gleamed under electric light. Somewhere inside that housing were secrets worth more than gold. Secrets about high-temperature alloys and cryogenic fluid dynamics and precision manufacturing. Secrets that 3 major powers were fighting to possess in the opening moves of a new kind of war. A war fought not with bullets, but with engineering knowledge. A war Britain was losing before most people knew it existed. He thought about the 3 engineers who died in June. Good men, experienced men. Killed by a pump that failed because British metallurgy was not good enough. British manufacturing was not precise enough. British engineering was not sophisticated enough. Killed by inadequacy. This German pump represented the knowledge needed to prevent more deaths, but it also represented something darker. This pump was developed at Peenemünde by engineers who knew their creation would kill civilians, who designed it anyway, who perfected it, who made it work so flawlessly that it could deliver a 1-ton warhead 300 kilometers with mechanical precision. Thousands died in London, Antwerp, Liège, Paris, killed by engineering excellence applied to murder. Now Lubbock was supposed to learn from that excellence, copy it, improve it, apply it to British weapons that would kill someone else's civilians in some future conflict. The morality was complicated. The necessity was not. Lubbock walked to the examination table, placed his hand on the turbopump housing. The metal was cold. He looked at Ashford. I will need a team. Materials specialists, machinists, technical illustrators. You have authorization to requisition whatever you need. I will need access to German technical documents, everything we captured. Arranged. Files are being transferred from London. Should arrive tomorrow. I will need test equipment, high-temperature furnace for materials analysis, precision measuring instruments, X-ray equipment to examine internal structures without full disassembly. Submit a requisition list. Priority approval. Lubbock nodded slowly. 6 weeks to unlock secrets that Germany spent years developing. 6 weeks to assess whether Britain could compete with Soviet and American programs. 6 weeks to determine if British rocket engineers were talented enough, disciplined enough, resourceful enough to close a technology gap that felt impossibly wide. He looked down at the turbopump again. The Germans had broken the laws of physics. No. They had obeyed the laws more precisely than anyone else, had pushed materials to absolute limits, had manufactured components to tolerances that seemed impossible, had operated in a regime where one mistake meant instant catastrophic failure, and they had succeeded. Lubbock picked up a notebook from the table, opened it to a blank page, wrote the date, September 14th, 1945. Below that he wrote, Examination of German V-2 turbopump assembly, serial B47331. Then he wrote 3 questions. 1. What materials and manufacturing methods enable operation at observed conditions? 2. Can British industry replicate these methods with available resources? 3. If not, what must Britain develop to achieve equivalent capability? He looked at the 3 questions for a long moment. Then he added a 4th question underneath. 4. What did the German engineers know that we do not? That was the real question. That was the question that would haunt him for the next 6 weeks and possibly the rest of his career. What did they know? And how much of that knowledge died with them in the bombing of Peenemünde? How much was captured by Soviets and Americans? How much was lost forever? And how much could be recovered from this single turbopump sitting on an examination table in an English laboratory, waiting to reveal its secrets to whoever was skilled enough to ask the right questions? Lubbock began his work. The turbine blade should not exist. Lubbock held it between thumb and forefinger, rotating it slowly under the magnifying lamp. The blade was 48 millimeters long, 12 millimeters wide at the base, tapering to 6 millimeters at the tip, curved like an airfoil. This single blade, one of 72 mounted on the turbine wheel, had survived conditions that killed 3 British engineers in June. Those men died when their test pump exploded after 8 seconds of operation. This German blade ran for 63 seconds at 750 degrees Celsius without even warping. The metal gleamed under the light. Beautiful, lethal, perfect. Lubbock carried the blade across the laboratory to the metallurgical testing station. Dr. Catherine Wells waited there, arms crossed, jaw tight. Wells was the senior metallurgist assigned to his team. Age 34, Cambridge Ph.D., worked at Royal Arsenal Woolwich developing armor steel during the war. She had examined preliminary samples from the turbopump yesterday and sent Lubbock a 2-word assessment. Not possible. Now she took the blade from his hand without speaking, held it up to the light, examined the surface with a jeweler's loupe. Her expression was unreadable. Lubbock knew why. Wells lost her younger brother in a V-2 attack on London, March 8, 1945. He was 19 years old, home on leave from the Navy. The rocket hit his neighborhood at 11:47 in the morning, killed 23 people instantly. Her brother was one of them. Now she was being asked to analyze the weapon that murdered him, asked to admire the engineering, asked to help Britain copy it. She had not mentioned her brother once since joining the team, but Lubbock saw it in her eyes every time she looked at a German component. Rage, grief, professional duty crushing both emotions down into cold, focused silence. Wells placed the blade in a specimen holder without ceremony. I need 2 hours for sample preparation. Take whatever time you need. 2 hours. She turned her back, began cutting a thin cross-section using a precision saw. The screech of the blade-cutting metal was the only sound in the laboratory. Lubbock left her alone. He spent the next hour examining the liquid oxygen pump impeller. The impeller was a centrifugal disc, 280 millimeters diameter, with 8 curved vanes machined into the surface. At 3,800 RPM, this disc accelerated liquid oxygen from 0 velocity at the center to 180 meters per second at the rim. The centrifugal acceleration was 14,000 times gravity. The stress trying to tear the impeller apart was 280 megapascals. One flaw, One crack, one impurity in the metal, and the impeller would disintegrate into shrapnel moving faster than rifle bullets. The pump housing would rupture. Liquid oxygen would spray into the turbine section. The turbine operated at 750 degrees Celsius. Oxygen meeting that temperature would ignite explosively. Everyone within 20 meters would die instantly. This impeller showed no flaws. Lubbock had been examining it for 3 days using every inspection method available. Optical microscopy, X-ray imaging, ultrasonic testing, dye penetrant. Every test showed the same result. Perfect. No cracks, no voids, no inclusions. Surface roughness measured 0.4 microns, mirror smooth. British machine tools produced surface finishes around 3 to 5 microns at best. Achieving 0.4 microns required precision grinding and polishing far beyond standard practice. The Germans had done it anyway, done it thousands of times, manufactured thousands of these impellers to impossible specifications. He turned the impeller over, examining the vane edges under magnification. Still sharp, not rounded by erosion despite operating in liquid oxygen, one of the most reactive substances in existence. The material was aluminum-bronze alloy. Chemical analysis showed 88% copper, 9% aluminum, remaining percentages iron and nickel. Good corrosion resistance, good low-temperature properties. But operating at 14,000 times gravity in liquid oxygen at minus 183 degrees Celsius was beyond aggressive. It was insane. It should have failed. It did not fail. Behind him, Wells called out, "Sample is ready." Lubbock returned to the metallurgical station. Wells had mounted the prepared blade cross-section under the microscope, applied etching solution to reveal the grain structure. She gestured at the eyepiece without speaking. Lubbock looked. The etched surface showed the internal crystalline structure of the metal. In normal high-temperature alloys, grains were typically 20 to 50 microns across. Larger grains meant weaker material at high temperature. This blade showed grains averaging 8 microns, impossibly fine. At 750 degrees Celsius, grains should grow rapidly. Something was pinning them, preventing growth, maintaining strength. Lubbock looked up. "What am I seeing?" Wells handed him a chart showing chemical composition analysis. Nickel-based superalloy, 62% nickel, 19% chromium for oxidation resistance, 9% molybdenum for strength, 3% titanium, 2.8% aluminum. The titanium and aluminum form intermetallic precipitates. Gamma prime phase. They pin grain boundaries, prevent grain growth at high temperature. "Can we make this alloy?" Wells laughed. It was a harsh sound, no humor in it. "We published papers about gamma prime precipitation in 1938. We know the theory. We know it works. We have never successfully manufactured it at production scale." "Why not?" "Because getting the chemistry right requires control we do not have. The titanium and aluminum percentages must be exact within 0.1%. The heat treatment must be precise within 5 degrees Celsius. One mistake and the precipitates do not form correctly. The material fails. Our current superalloy production has 40% rejection rate. 4 out of 10 batches fail specification. We scrap them and try again." "And the Germans?" Wells tapped the blade with her fingernail. Hard. The sound was sharp, metallic. "The Germans manufactured thousands of these blades. Consistent quality, production scale. They did not solve the problem we are struggling with. They solved it years ago and moved on to mass production. We are not behind. We are not catching up. We are so far behind we cannot even see them anymore." Lubbock felt something cold settle in his stomach. How far behind? 10 years. Minimum. Possibly 15. She picked up the blade again, turned it over in her fingers. "You know what the worst part is? This blade was manufactured by people who knew it would kill civilians, who designed it anyway, who made it perfect, who achieved engineering excellence in service of murder. And now I am supposed to admire it, supposed to learn from it, supposed to copy it so we can build our own rockets to kill someone else's civilians in the next war. This blade killed my brother, and I am holding it like it is a treasure instead of evidence of a war crime." Her voice had not risen. The words came out level, controlled, precise, but her hands were shaking. Lubbock said nothing. There was nothing to say. Wells placed the blade down carefully, turned away, walked to the window, stared out at the Buckinghamshire countryside. Lubbock gave her space. He spent the next hour examining bearing components. The turbopump bearings operated in liquid oxygen at minus 183 degrees Celsius. Bearings required lubrication. Oil was impossible. Oil would freeze solid and then explode on contact with oxygen. The German solution was elegant and terrifying. The bearings were lubricated by the liquid oxygen itself. The bearing surfaces were coated with ceramic, aluminum oxide, applied by plasma spray process. The coating was 0.15 millimeters thick, uniform across the entire bearing surface. Plasma spray was experimental technology in 1945. Britain had one research laboratory with prototype equipment. Germany had production plasma spray systems manufacturing thousands of coated bearings. Another technology gap. Another development program requiring years. Lubbock made notes. The list of required capabilities was growing impossibly long. Advanced superalloys with controlled precipitation hardening, precision machining to submicron surface finish, production-scale plasma spray coating, electron beam welding for joining dissimilar metals without contamination, quality control systems capable of 8% rejection rates instead of 40%. Each item represented years of development, millions of pounds in investment, thousands of skilled workers, and time, always time, time Britain did not have. The door burst open. Wing Commander Ashford strode in, face grim, holding a telegram. "We have a problem." Lubbock straightened. "Sir?" "Soviet Union announced successful test firing of a captured V-2 rocket. Yesterday, from a facility near Moscow. Complete success. 300-kilometer range. They are claiming full operational capability within 6 months." The cold feeling in Lubbock's stomach became ice. 6 months. The Americans tested their first captured V-2 3 weeks ago. Also successful. They have Werner von Braun and his entire engineering team working for them. 120 German rocket specialists. Complete technical documentation. They are planning test launch program of 100 rockets over the next year. Ashford dropped the telegram on the examination table. Meanwhile, Britain has one turbopump, partial documentation, no German engineers, and a team that is discovering we are 15 years behind in materials technology. The minister wants updated assessment. He wants to know if we can compete. I need an answer. Lubbock looked at the disassembled turbopump components spread across multiple tables. Turbine blades made from alloys Britain could not manufacture. Impellers machined to tolerances Britain could not achieve. Bearings coated with ceramics using processes Britain barely understood. Each component a masterpiece of engineering. Together they represented a level of systematic technological sophistication that Britain simply did not possess. Wells returned from the window. She looked at Ashford, then at Lubbock, then at the turbine blade still sitting on the examination table. "Can we compete?" she asked quietly. "That is the question, is it not?" Lubbock chose his words carefully. "Not in the short term. We lack fundamental capabilities, materials, manufacturing, quality control. We cannot replicate this pump with current resources. Attempting to do so will result in failures, possibly fatal failures. Long term? Possible. With sustained investment, 5 to 10-year development program, assuming adequate funding and priority." Ashford's expression darkened. 5 to 10 years. The Soviets will have operational missile forces in 6 months. The Americans in less than a year. You are telling me Britain will be defenseless. I am telling you that trying to skip development steps will kill British engineers the same way it killed the 3 men in June. This technology was not built in months. It was built over 8 years by thousands of German engineers with unlimited resources and slave labor from concentration camps. Wells flinched. Ashford caught it. "Dr. Wells, you have something to add?" Wells looked at the turbine blade. When she spoke, her voice was controlled again. Professional. "Sir, if I may, we are asking the wrong question. Can we compete? Is not the relevant question. We cannot compete. We lost this race before it started. The relevant question is, what can we salvage? What can we learn that advances British capability, even if we never match German or Soviet or American programs? She picked up the blade. This blade represents knowledge, specific knowledge about high-temperature metallurgy, about precision manufacturing, about quality control. That knowledge has value independent of whether we build V-2 copies. We can apply it to jet engines, to industrial turbines, to a dozen civilian and military applications. We cannot win the rocket race, but we can ensure this analysis is not wasted. Ashford considered this in silence. Finally, he nodded. Continue your analysis. Full documentation of all components. I want every material identified, every manufacturing process characterized, every design principle extracted. Focus on what can be applied to other programs. Jet engines are priority. Is that understood? Yes, sir. Ashford left. The laboratory fell silent again. Lubbock looked at Wells. Thank you. Wells shook her head. Do not thank me. I am not doing this for Britain's military capability. I am doing this because my brother died from German engineering excellence, and I will not let his death be meaningless. If we learn something from this analysis that saves lives in the future, even one life, then his death purchased something. That is the only way I can make sense of it. The only way I can hold this blade without screaming. She placed the turbine blade down and returned to her microscope. Lubbock understood. They were not going to win the rocket race. They were going to extract every scrap of knowledge from this turbopump and apply it elsewhere. They were going to turn a weapon into understanding. They were going to salvage what they could from 15 years of German technological advantage, purchased with slave labor and aimed at civilians. It was not victory. It was not even competition. It was survival. Lubbock picked up his notebook and continued documenting measurements. Outside, October rain began falling on the Buckinghamshire countryside. Inside the laboratory, 2 British engineers worked late into the night, learning secrets from a machine designed to kill them. The pump exploded at 3.2 seconds. Lubbock stood in the concrete bunker watching through armored glass as flame and shrapnel tore through the test cell. The turbopump they had spent 6 months building disintegrated. Metal fragments punched through reinforced concrete. The blast wave hit the observation window. A crack appeared in the supposedly shatterproof glass, spreading like lightning across Lubbock's field of vision. For one terrible moment, he thought the window would fail completely. 3 tons of high-velocity debris would fill the bunker. He would die the same way Thompson and Morris and Fletcher died in June. The crack stopped spreading. The window held. Barely. Fire suppression systems activated, flooding the test cell with foam. When the smoke cleared, nothing remained except twisted wreckage and the spiderweb crack in the glass. Lubbock touched the crack with his fingertip. Cold glass. Warm finger. The difference between observing death and experiencing it. 3 millimeters of fractured glass. He checked his stopwatch. 3.2 seconds. The German pump ran for 63 seconds. British engineers had achieved 5% of that endurance. 5%. His hands were shaking, not from fear. He had been afraid during the explosion. Now the fear had drained away, replaced by something worse. Exhaustion. Bone-deep exhaustion that came from 15 months of failure. This was the 4th attempt. December 1946, first test, 2.8 seconds, turbine wheel disintegration. March 1947, second test, 4.1 seconds, housing thermal cracking. July 1947, third test, 2.1 seconds, bearing seizure fire. That explosion had sent a technician named Robert Clark to hospital with second-degree burns and permanent hearing loss in his left ear. Clark was 24 years old. He would never work around rocket engines again. Now, November 1947, fourth test, 3.2 seconds, impeller hub failure. 4 attempts, 4 failures, 1 injured technician, 15 months consumed, 6 engineers assigned full-time. Estimated cost so far, £280,000. Results: a test cell full of debris and a cracked observation window, and the growing realization that Britain could not replicate German technology. Lubbock left the bunker, walked across the test facility grounds toward the engineering office. Cold December rain soaked through his coat. His head throbbed. The stress headaches had become constant 3 months ago. Medication barely helped. His doctor suggested rest. Lubbock suggested his doctor try telling that to the Ministry of Supply. Behind him, cleanup crews were cataloging fragments, documenting failure modes, preparing for a fifth attempt if there was a fifth attempt. Funding was becoming critical. The Rocket Propulsion Development Program received £500,000 in 1946, more than half gone. Results achieved: 0 functional turbopumps, 0 successful tests longer than 5 seconds, 0 progress toward operational capability, 1 hospitalized technician, 1 cracked observation window, 1 engineer with constant headaches who had not seen his family for more than 6 hours at a time in 4 months. His wife had stopped asking when he would be home. She just left dinner in the oven and went to bed. Some mornings he found notes. Milk is low. Telephone bill is due. Your daughter asked about you. Simple factual statements. No emotion, no accusation, just facts, like test reports. Cold, precise, distant. He entered the engineering office. Catherine Wells sat at her desk surrounded by metallurgical reports. She looked up, saw his expression, and knew. How long? 3.2 seconds. The window cracked. Wells's eyes widened. How badly? Spiderweb pattern. Held but compromised. They will replace it before the next test. If there is a next test. If there is a next test. Wells stood, walked to the window overlooking the test facility. Rain streaked the glass. We cannot do this. We do not have the capability. We are trying to compress 8 years of German development into 18 months with a fraction of their resources, and people are getting hurt. Clark still cannot hear properly. You look like you have not slept in weeks. How much longer do we keep pretending this is achievable? Lubbock sat down heavily. What choice do we have? The Americans have launched 67 V-2 rockets. 67. They have Werner von Braun and his entire team. They are learning by doing. The Soviets captured Peenemünde, have the factories, have 200 German engineers. Britain has 1 captured turbopump and a test program that keeps destroying equipment and injuring people. So we admit defeat. So we change strategy. Wells turned from the window. Explain. We stop trying to copy German hardware and start applying German knowledge to British designs. Design around our limitations instead of trying to overcome them in impossible timelines. The door opened. Wing Commander Ashford entered, coat dripping, face grim. He looked at the debris visible through the window, at Lubbock, at Wells. I saw the observation window. Engineering says it needs complete replacement. Add £3,000 to program costs. How long did the pump run? 3.2 seconds. Impeller hub failure from casting voids below our detection threshold. Ashford sat down, pulled out a telegram, placed it on the desk. Soviet Union deployed operational R-1 missiles to military units in Ukraine yesterday. R-1 is their designation for V-2 copies. Operational. Deployed. Targeting range covers all of Western Europe. The Americans successfully tested a V-2 from USS Midway aircraft carrier last week. Shipboard launch capability. Global reach. Meanwhile, Britain cannot keep a turbopump operating for 5 seconds. He looked at Lubbock directly. Your daughter is 7 years old, correct? Lubbock was caught off guard by the question. 8. She turned 8 in September. Does she know what you do? She knows I work with rockets. Does she know you have not been home for dinner in 4 months? That you have missed her last 2 birthdays because of test schedules? That your wife writes you notes because you are never awake at the same time? Lubbock felt something cold in his stomach. Sir, I do not see how... The minister asked me that question this morning. Asked if I thought the program was worth destroying the families of the engineers working on it. Asked if I thought it was worth injuring technicians like Clark. Asked if I thought it was worth £280,000 with 0 results. I did not have a good answer. Silence filled the office. Rain drummed against windows. Somewhere outside, crews were loading test cell debris into trucks. Wells broke the silence. Her voice was controlled, precise, clinical. Sir, permission to speak frankly. Ashford gestured. Please. We are approaching this wrong. We are trying to copy German results without understanding German process. The Germans did not build a working turbopump on the first try. They failed dozens of times over 8 years with unlimited resources and slave labor from concentration camps. We have 18 months and a shrinking budget, and we are trying to match their final design. It is impossible. We need to stop. You recommend cancellation? I recommend redesign. Stop building V-2 copies. Use German knowledge to develop British designs suited to British manufacturing capabilities. Lower performance targets. Achievable specifications. Something that actually works instead of something that matches German performance and keeps exploding. Ashford leaned back. The minister wants competitive performance. The minister can have competitive performance in 10 years or adequate performance in 3 years. Those are the options. We do not have German engineers. We do not have their materials. We do not have their manufacturing precision. We cannot compress a decade of their development into 2 years of ours. Physics does not work that way. Engineering does not work that way. We can keep destroying equipment and injuring people trying to achieve impossible goals, or we can set achievable goals and actually accomplish something. Ashford looked at Lubbock. Your assessment? Lubbock thought about the cracked observation window, about Robert Clark's burned hands and permanent hearing loss, about his 8-year-old daughter who barely knew him anymore, about his wife's factual notes devoid of emotion, about 4 test failures in 15 months, about the German turbopump that ran for 63 seconds while British pumps exploded after 3. Dr. Wells is correct. We cannot match German specifications with British capabilities. We need to design British rockets that Britain can actually build. Lower performance is acceptable if the alternative is continued failure. A rocket that flies 200 kilometers is infinitely more useful than a rocket that explodes on the test stand or blinds technicians or fractures observation windows. Ashford picked up the telegram, read it again, placed it down. Intelligence reports that Egypt and Argentina are hiring German rocket engineers, former Peenemünde staff. They are offering salaries we cannot match, promising to continue their work under new flags. Within 5 years, half the nations in the world will have rocket capability purchased from Germans who built weapons for Hitler. Britain will be surrounded by threats while we argue about whether we can match 1945 German technology in 1947. He stood. I will present redesign proposal to the ministry. No promises. They may cancel everything. But I will argue for achievable goals over aspirational fantasies. Dr. Lubbock, I want detailed design specifications for a British turbopump. Lower performance, British materials, British manufacturing methods, timeline and costs. 1 week. Yes, sir. And Dr. Lubbock, after you finish that report, go home. Have dinner with your daughter. Sleep in a real bed. See your wife. The program is not worth destroying your family. We are building weapons to protect British families. If we destroy our own families building them, what exactly are we protecting? Ashford left. Lubbock sat in silence. Wells returned to her desk, began pulling reference materials. Well, she said quietly, we are officially admitting defeat in the race to copy V-2 technology. We are admitting reality. Same thing. Lubbock pulled out the complete documentation of the German turbopump. 2 years of analysis, thousands of measurements. That knowledge was still valuable even if they were not building copies. He spread technical drawings across the desk, began sketching a British design, lower speed, reduced flow, materials from British suppliers, tolerances achievable with British tools, conservative margins. It would not match German performance, but it might actually work, and nobody would get burned, and observation windows would not crack, and 8-year-old daughters might occasionally see their fathers. Wells joined him, pointed at his sketch. Turbine diameter is too small for that flow rate. Lubbock erased, redrew. Larger diameter then, 320 millimeters. Heavier pump. Acceptable. We are not constrained by German size limits. They worked through the afternoon. The design that emerged was different from the German pump. Larger, heavier, less efficient, but buildable. Actually buildable. By evening, they had preliminary specifications. Turbopump mass 480 kilograms versus German 340. Rotational speed 2,600 RPM versus German 3,800. Propellant flow 85 kilograms per second versus German 125. Estimated development 30 months. Estimated cost £420,000. Performance adequate for 180 kilometer range, 750-kilogram warhead, not as capable as V-2, but achievable. Lubbock compiled specifications into a report, 47 pages. He finished at 10 p.m. Wells had left at 8. The office was empty. He read through the report one final time. This was admission of British technological inferiority, admission they could not match what their enemies built. It was humiliating. It was realistic. He signed the report, placed it in Ashford's inbox, turned off the light. Outside, stars were visible through breaking clouds. Lubbock walked to his car, drove home. The house was dark except for one light in the kitchen. His wife had left dinner in the oven. Shepherd's pie. Cold now. A note sat on the counter. Your daughter has a school concert Thursday at 3 p.m. She asked if you could come. I told her probably not. Lubbock crumpled the note, threw it away, pulled out a fresh sheet of paper, wrote, I will be there. Thursday 3 p.m. Promise. He placed the note where his wife would see it in the morning. Then he ate cold shepherd's pie, went upstairs, looked in on his sleeping daughter, 8 years old. He had missed her last 2 birthdays, had missed her school concerts, had missed dinner 4 months running. For what? For a test program that kept exploding. For trying to match technology Britain could not replicate. For breaking observation windows and burning technicians and accomplishing nothing. Tomorrow, he would submit a report admitting Britain could not copy German rockets, could only learn from them, could only build inferior versions suited to British limitations. It was defeat. But defeat with eyes open was better than continued failure with eyes closed. Lubbock returned downstairs, fell asleep on the sofa still wearing his clothes. He dreamed of explosions and cracked glass and his daughter asking where her father was. When he woke at dawn, the headache was still there. But for the first time in months, he knew what he was building toward. Something achievable, something real, something worth protecting his family for instead of destroying his family for. Britain would build rockets, just not German rockets. That would have to be enough. The German walked into the laboratory like he owned it. Dr. Werner Hartmann, 52 years old, former technical director at Peenemünde Rocket Development Facility, current employee of the British government under contract number 47/B/328, salary £800 per annum plus housing, 3 times what Lubbock earned. Hartmann carried a leather briefcase and wore an expensive suit that looked wrong in the utilitarian laboratory. His shoes were polished. His tie was silk. He looked prosperous, comfortable, successful. He looked like someone who had not lost a war. He extended his hand. Dr. Lubbock, I understand you have been experiencing difficulties with turbopump development. Lubbock did not shake the hand immediately. He looked at it. Clean. Manicured nails. No scars. No burns. The hand of someone who worked with pencils and paper, not metal and fire. The hand of someone who designed weapons that killed 2,654 British civilians. After a long moment, Lubbock shook it briefly. The handshake was perfunctory. Professional courtesy. Nothing more. Dr. Hartmann, welcome to Westcott. Hartmann smiled. It did not reach his eyes. Please call me Werner. We will be working together closely for the next 30 months. Formality seems unnecessary. The door from the materials laboratory opened. Catherine Wells entered carrying a stack of metallurgical reports. She stopped when she saw Hartmann. The reports slipped from her hands. Papers scattered across the floor. She stared at Hartmann. He stared back. The silence stretched. Wells bent slowly, began gathering papers with shaking hands. The tremor was visible. Obvious. She tried to control it, could not. The papers rustled. Some fell again. Lubbock moved to help her. She waved him away sharply, gathered the papers herself, stood. Her face had gone carefully blank. Professional mask. But her hands still shook. Lubbock knew what was behind that mask. Her brother, 19 years old, killed by V-2 rocket on March 8, 1945. One of 2,654 civilians murdered by weapons this man helped create. Hartmann had not personally launched the rocket that killed her brother, had not personally targeted civilians, had only designed the propulsion system that made the murder possible, only calculated the combustion dynamics and turbopump specifications and propellant flow rates, only turned abstract mathematics into 300 kilometers of ballistic trajectory, terminating in explosion and death. Only applied genius to murder. Lubbock made introductions. His voice sounded distant to his own ears. Dr. Werner Hartmann, Dr. Catherine Wells, senior metallurgist. Hartmann extended his hand. Wells looked at it. 3 seconds passed. 4, 5. She turned and walked back into the materials laboratory without speaking, without touching him. The door closed behind her, not slammed, closed with careful, deliberate control. That control was worse than anger. Anger passed. Control lasted. Awkward silence filled the main laboratory. Hartmann lowered his hand slowly. For just a moment, something crossed his face. Not quite guilt, not quite shame. Recognition, perhaps. Awareness. He knew what they thought of him. He was correct. "I see," he said quietly. "Well, perhaps we should begin with technical review." Lubbock gestured at the examination tables covered with components from their failed turbopump tests. Wreckage. Evidence of 15 months of failure. This is where we are. Hartmann walked along the tables, examining destroyed impellers, cracked housings, seized bearings. His expression remained professional, controlled, but Lubbock caught subtle reactions. A slight head shake here, a barely audible sigh there. The reactions of someone looking at work of amateurs who did not understand what they were attempting. After 10 minutes, Hartmann turned. "May I speak candidly?" "Please." "This is not turbopump development. This is trial and error without understanding underlying principles. You are attempting to copy V-2 hardware without comprehending the engineering knowledge that created it. Every failure I see here was predictable, preventable. The impeller hub cracking from microscopic voids, the bearing seizures from uneven ceramic coating, the thermal stress fractures from inadequate weld procedures. We encountered these exact failures at Peenemünde between 1938 and 1941. We solved them. You are repeating mistakes we made a decade ago." Lubbock felt heat rising in his face, professional pride wounded. "We documented the German turbopump completely, analyzed every material, measured every dimension, applied British manufacturing capabilities, and that is your error. You cannot apply British manufacturing capabilities to German engineering specifications. The specifications require German capabilities, precision machining to tolerances of 0.02 millimeters, advanced metallurgy with controlled gamma prime precipitation, quality control that rejects 40% of components as inadequate. You do not have these capabilities, so you attempted substitutions, used available materials instead of correct materials, accepted looser tolerances because your machine tools cannot achieve tighter ones, hoped it would somehow work. It did not work. It will never work this way." The anger flared hot. Lubbock stepped closer, voice rising. "We have been working on this problem for 2 years, lost 1 man to permanent injury, spent £280,000, cracked an observation window that nearly killed me. You walk in here wearing a suit that costs more than I earn in 6 months with your government salary that is triple mine, and you lecture me about mistakes? You built weapons that killed thousands of civilians, murdered my countrymen, murdered her brother." He gestured toward the materials laboratory. "And now I am supposed to stand here politely while you criticize British engineering?" Hartmann's expression did not change. His voice remained level. "Yes, because I know how to build rockets that function, and you do not. Your government hired me for exactly this knowledge. If you find that distasteful, take it up with your Ministry of Supply. They wrote the contract. They negotiated the salary. They decided German expertise was worth purchasing, despite the political complications. I am here because Britain needs what I know. If you do not want German help, continue failing alone. I will collect my salary either way." The words hung in the air. Cold. True. Devastating. Lubbock wanted to hit him, wanted to throw him out of the laboratory, wanted to refuse his help and prove that British engineers could solve this without Nazi assistance. But they could not. 2 years proved they could not. 4 test failures, 1 injured technician, an observation window cracked by explosion, a redesign that abandoned any hope of matching V-2 performance. They needed help, needed expertise, needed Germans. It was galling. It was humiliating. It was necessary. It was reality. Lubbock took a breath, controlled his voice with effort. What do you need? Complete documentation of your redesign specifications, all test data from your 4 failures, access to your manufacturing facilities and suppliers. And the woman, Dr. Wells, needs to work with me despite her personal feelings. I understand she lost family to V-2 attacks. Many people lost family. Many Germans lost family too. To Allied bombing, to ground combat, to the consequences of a war we all participated in. The war is over. The work continues. She can hate me on her own time. During work hours, she must be professional. I will speak with her. Today. We have 30 months to develop functional turbopump. Timeline is already aggressive. Delays from personal animosity are unacceptable. Hartman opened his briefcase, extracted a folder thick with technical documents. These are V-2 development reports from Peenemünde. Test failures from 1938 to 1943. Detailed analysis of every problem we encountered and every solution we developed. Metallurgical specifications. Manufacturing procedures. Quality control protocols. Everything Britain needs to avoid repeating our mistakes. Study these. We will discuss implementation tomorrow morning at 8 o'clock. He placed the folder on Lubbock's desk. Then, more quietly, I know what you think of me. You are correct. I built weapons that killed civilians. I did the calculations that made the murders efficient. I cannot undo that. Cannot justify it. Can only offer the knowledge I gained in service of your country now instead of mine. If that is insufficient, tell your government. They can cancel my contract. I have other offers. Egypt, Argentina, Soviet Union, indirectly. Everyone wants German rocket expertise. Britain hired me first. If Britain does not want me, someone else will. He left. The laboratory fell silent. Lubbock stared at the folder. Answers. Years of German development compressed into documentation. Knowledge purchased for £800 annually, and the moral compromise of hiring men who built weapons that murdered civilians. He opened the folder. The first document was titled Turbopump Failure Analysis, November 1938. Impeller hub cracking due to microscopic casting voids. Detailed technical German with English translation. The report described a test failure almost identical to their November 1947 disaster. Housing thermal cracking. Impeller failure. The Germans had encountered this exact problem in 1938, solved it by 1939 using improved casting procedures and X-ray inspection equipment capable of detecting voids smaller than 0.5 millimeters. Britain encountered it in 1947, had not solved it by 1948, 9 years behind. Lubbock spent 2 hours reading. Each document showed systematic engineering. Problem identified. Root cause analyzed using metallurgical testing and stress calculations. Solution developed. Multiple approaches tested. Optimal solution selected. Testing validated performance. Knowledge captured in detailed reports. The Germans had failed repeatedly, but learned from every failure. Built institutional knowledge. Created engineering database that made subsequent development faster, more efficient. Britain had scattered notes, individual insights, incomplete documentation. No systematic knowledge capture. Every engineer solving problems in isolation. No institutional learning mechanism. The contrast was professionally humiliating. Lubbock found Wells in the materials laboratory, examining turbine blade cross-sections under the microscope. She did not look up when he entered. Her hands had stopped shaking, but her jaw was tight. He is gone? For today. Catherine, we need to talk. About working with the Nazi who designed rockets that killed my brother. Yes. Wells placed the microscope sample down with extreme care. Turned. Her eyes were dry, but her voice was raw. I cannot do this. I cannot work beside that man. Cannot listen to him explain engineering principles with that calm professorial voice. Cannot watch him mark up our drawings. Cannot pretend the past does not exist. Cannot be professional about murder. The war is over. Tell that to my brother. Tell that to the 2,654 people who died from V-2 attacks. Tell that to the thousands more who died from V-1 flying bombs and Luftwaffe raids and U-boat torpedoes and concentration camps and every other application of German engineering genius to systematic murder. Tell them the war is over, so we should forgive and hire the people who killed them and pay them 3 times what we earn, and learn from them and thank them for their expertise. I am not asking you to forgive. I am asking you to work for him, under his direction, learning from his expertise, applying his knowledge, becoming his student. The man whose rockets killed my brother becomes my teacher. Do you understand how that feels? Lubbock sat down heavily. No, I did not lose family. I lost time and pride and sleep and 2 years of my life trying to replicate what he built. But I did not lose someone I loved. Wells laughed bitterly, no humor in the sound. You know what the worst part is? He is right. I looked at our failed components this morning, looked at his reputation before he arrived. Werner Hartmann was technical director of V-2 propulsion system development, published 17 papers on liquid rocket engines before the war, one of the leading experts in combustion dynamics and turbomachinery in the world. He knows more about turbopumps than everyone at Westcott combined, more than everyone in Britain combined, probably. If we want functional British rockets, we need his knowledge, need him to teach us what he knows, need to become his students whether we like it or not. The man who built weapons to kill us becomes our teacher. The moral inversion is staggering. She turned back to the microscope. I will work with him, professionally. I will learn what he knows. I will help develop functional turbopump using his expertise. I will apply his recommendations and validate his calculations and implement his manufacturing procedures. But I will never like it. Never forget it. Never forgive it. Never pretend that hiring Nazis to teach us their secrets is anything except moral failure purchased with practical necessity. Every time I see him, I will see my brother's grave. Every time he explains an engineering principle, I will hear the explosion that killed 23 people on March 8th. Every time he solves a problem that we could not solve, I will feel the shame of needing help from someone who used his genius to murder civilians. If you expect me to set that aside and smile and call him Werner and share tea breaks and pretend we are colleagues working toward common goals, you are expecting too much. I expect you to be professional. Then you will get exactly that. Professional. Nothing more. Nothing less. Cold. Functional. Efficient. Like German engineering. The next morning, Hartmann returned, brought 3 more German engineers. Kurt Schneider, propulsion specialist, age 47. Hans Weber, materials expert, age 51. Friedrich Müller, manufacturing engineer, age 44. All former Peenemünde staff. All now British government contractors earning £600 to £850 annually. More than most British engineers with equivalent experience. They set up in the conference room, spread technical drawings across tables, arranged themselves on one side. British team sat opposite. Physical division. Symbolic. The first hour was systematic review of British test failures. Hartmann went through each methodically using a red pen to mark drawings. December 1946. Failure. Turbine wheel grain structure inadequate due to incorrect heat treatment temperature. Should be 150 degrees Celsius for 4 hours, not 100 degrees for 3 hours. March 1947. Failure. Housing weld joint design fundamentally flawed. Thermal expansion coefficient mismatch between weld metal and base metal creates stress concentration. Requires electron beam welding, not conventional arc welding. July 1947. Failure. Ceramic coating thickness variation exceeds tolerance. Requires plasma spray equipment with automated traversing mechanism and real-time thickness monitoring. Manual application inadequate. November 1947. Failure. Impeller casting voids below detection threshold of British X-ray equipment. Requires higher energy, X-ray source minimum 250 kilovolts, and digital image processing to detect 0.3 millimeter voids. Each explanation was technical, precise, professorial. Not condescending, but the implication was devastating. Britain was repeating mistakes Germany solved years ago using equipment and processes Britain did not possess. Wells sat rigid, taking notes in perfect handwriting, face expressionless. The second hour was redesign review. Hartmann examined British specifications for the lower performance turbopump. nodded slowly. This is sensible approach. You cannot build V-2 copy with current capabilities. You can build British rockets suited to British manufacturing. This design is achievable with modifications. He pulled out the red pen again, began marking. Here, impeller blade angle is 32 degrees but should be 38 degrees for this flow rate, and rotational speed, incorrect angle creates flow separation and reduces efficiency by 18%. Here, turbine nozzle throat diameter is 8.2 millimeters, but should be 9.4 millimeters for proper steam expansion ratio. Undersized throat causes back pressure that reduces power by 12%. Here, bearing load calculation assumes steady-state thrust, but ignores startup transients that triple the load for first 2.3 seconds. Bearing will fail during startup cycle. Here, housing bolt material thermal expansion coefficient, 12 times 10 to the minus 6 per degree Celsius, does not match housing material 23 times 10 to the minus 6, creates stress concentration during thermal cycling, bolts will loosen or shear. He marked 47 issues in 35 minutes. Each mark represented a problem that would cause test failure or performance degradation. Each mark represented knowledge British engineers lacked. Each mark represented the value of hiring people who murdered your civilians to help you build weapons. By end of day, redesign had 47 modifications based on German recommendations. Lubbock compiled changes, ran new performance calculations. With modifications, predicted propellant flow, 91 kilograms per second instead of 85. Predicted operating life, 95 seconds instead of estimated 70. Predicted reliability, 94% instead of hoped for 85%. Timeline to functional hardware, 18 months instead of 30. Cost savings, approximately 140,000 pounds. The Germans were worth every pound of their salaries and the moral compromise of employing them. That night, Lubbock drove home, had dinner with his daughter, helped her with mathematics homework, read her a bedtime story about a princess and a dragon, tucked her in, kissed her forehead. She asked, "Daddy, did you build rockets today?" "Yes, sweetheart." "Will they go to the moon?" "Someday. Not yet, but someday. I want to go to the moon." "Maybe you will. Sleep now." He returned downstairs. His wife was washing dishes. She asked without turning, "How was work?" "We hired Germans to teach us how to build rockets." "Germans who built the V-2? "Yes." Long silence. Water running. Dishes clinking. Finally, "How do you feel about that?" Lubbock thought about Werner Hartmann's calm professorial lecture, about the 47 modifications that would make the redesign work, about Wells sitting rigid across the table from the man whose rockets killed her brother, taking perfect notes with trembling hands, about the moral compromise of hiring expertise from murderers, about paying them triple British salaries, about learning from them, about needing them. "I feel like we are doing what is necessary to protect our country, and I feel ashamed that what is necessary involves learning from people who killed our countrymen. Both things are true simultaneously. I do not know how to reconcile them. I am not sure they can be reconciled." His wife dried her hands, touched his face gently. "Maybe you are not supposed to reconcile them. Maybe you just carry both and do your job anyway. Maybe that is what living in the world after this war means. Carrying impossible contradictions and functioning despite them. Is that enough? It is what we have. It will have to be enough." Lubbock nodded, went to his study, reviewed the technical documents Hartmann provided. Page after page of systematic German engineering knowledge. Purchased, applied, necessary, shameful, both, all of it simultaneously. He worked until midnight, learning from teachers who built the weapons that nearly destroyed his country, so he could build weapons to protect it in the next war that was already beginning in the shadows of the Cold War. The moral calculus was impossible. The engineering was clear. Britain would build rockets. With German help. Because pride was less important than capability. Because losing was worse than compromise. Because the world did not care about your moral purity, only your strategic capability. The Germans taught them that lesson, taught it with V-2 attacks that killed thousands. Now they were teaching it again, differently, with technical documents and redesign consultations and 800-pound annual salaries and red pen marks on British drawings. Different lesson. Same teachers. Welcome to 1948. Welcome to the post-war world built on expertise of people who nearly destroyed the pre-war world. Welcome to the future where yesterday's enemies become today's consultants, and morality becomes luxury you cannot afford, and necessity becomes justification for everything. Lubbock closed the folder, turned off the light, went to bed. Tomorrow the work continued. Learning from Nazis, building rockets, protecting families, compromising principles, carrying contradictions, all of it required, all of it terrible, all of it the price of survival in a world where the next war was always coming, and the only question was whether you would be ready. The pump ran for 127 seconds. Lubbock watched from the observation bunker through the new reinforced window as the turbopump spun at 2,600 RPM, moving 91 kilograms of propellant per second without failure. The test cell instrumentation showed stable temperatures, pressures within specification, no vibration anomalies. At 65 seconds, the pump equaled German V-2 endurance. At 127 seconds, when fuel supply exhausted, the turbopump had operated twice as long as the weapon that nearly destroyed Britain. Shutdown procedure nominal. No explosions, no fires, no shrapnel. Just controlled shutdown of functional British turbopump running on British propellants in British test facility designed by British engineers with German guidance. November 18, 1950, 4 years and 6 months after the first catastrophic failure. 4 years and 6 months of explosions and injuries and cracked windows and sleepless nights and moral compromise. Success, finally, achieved. Lubbock turned to the assembled team. 12 British engineers, 4 German consultants, all watching data readouts in silence. When the last instrument reading stabilized, someone started clapping. The applause spread. Brief, restrained, British. Catherine Wells stood at the back, arms crossed. When the applause ended, she turned and left the observation room without speaking. Lubbock watched her go. Understanding. This was her success, but never her victory. Werner Hartmann examined data logs, made notes in his leather notebook, looked up with slight smile. Congratulations, Dr. Lubbock. Britain now possesses functional rocket propulsion capability. This turbopump meets all design specifications, exceeds several, ready for integration into complete engine system. The words were professional, correct, empty of emotion, just technical assessment, just facts. Lubbock ordered champagne, modest celebration. The team gathered in conference room. Toasts were made with careful, polite words. British engineers thanked German consultants. German consultants acknowledged British perseverance. Everyone drank quickly and left. Wells stood by the window holding untouched champagne, watching rain fall on test facility grounds. Lubbock joined her. Neither spoke for a long moment. Finally, "You should feel proud. Your metallurgical work made this possible." "I feel relieved. Relief is not the same as pride." She placed the glass down untouched. "Do not misunderstand. I am glad we succeeded. Glad British rocket program is viable. But I will never feel proud of success achieved by learning from Nazis. I will feel competent, successful, professionally satisfied, but not proud. Pride requires moral clarity. This situation has none. Only necessity and compromise and the knowledge that we accomplished what we had to accomplish regardless of how we felt about it. Catherine, my brother has been dead 5 years, 8 months, 10 days. Every day I have worked on technology descended from weapons that killed him. Every day I have learned from people who designed those weapons. Every day I have carried that. Today we succeeded. The weight is the same. Success does not make it lighter." She left. Lubbock stood alone with his untouched champagne. The celebration lasted 30 minutes. Everyone went home early. 3 weeks later, formal report delivered to Ministry of Supply. British rocket turbopump development completed successfully. Functional hardware demonstrated. Performance exceeds minimum specifications. Ready for integration. The minister sent congratulations. Authorized continued funding. Requested accelerated timeline. Hartmann's contract extended through December 1952. Increased salary. The work continued. By April 1952, complete rocket engine tested successfully. By November 1952, first full rocket system launched. Flew 78 kilometers. Impacted target zone. Britain had ballistic missile capability. The Germans prepared to leave in December. Final day was December 19, 1952. Cold morning. Frost on laboratory windows. Hartman packed his belongings. Leather briefcase. Technical notebooks. Personal items accumulated over 4.5 years. Lubbock found him in the office. "Your flight leaves at 3? "Yes. Argentina tomorrow morning. New project. Generous funding." "Will you miss this?" Hartman looked around the laboratory. "I will miss the engineering challenges, the problem solving. I will not miss the atmosphere. The British are very polite, very professional, very correct, and they hate us. Understandably. Working where you are hated is exhausting regardless of politeness. You knew it would be this way when you accepted the contract. Knowing and experiencing are different." "But yes, I knew." Lubbock extended his hand. "Thank you for your contributions. Britain's rocket program would not exist without your expertise." Hartman shook it. "You are welcome. Britain's engineers are capable. You needed knowledge, not talent. Now you have both. You will do well without us." He picked up his briefcase. Paused. "May I ask something?" "Yes. Do you think what we did here was right? Not technically, morally. Hiring us, learning from us, paying us well while knowing what we built before." Lubbock thought carefully. "I think it was necessary. Whether necessary and right are the same thing, I cannot say. We needed expertise. You had it. We made transaction. The morality of that transaction is question I cannot answer." Hartman nodded slowly. "Honest answer. Better than comfortable lie." He left the office, walked toward the exit. Catherine Wells was waiting in the corridor. She stood directly in his path, blocking. Hartman stopped. They looked at each other. Long silence. Finally, Wells spoke. Her voice was controlled but shaking slightly. "I need you to say it, just once, before you leave. Not philosophy about neutral technology. Not justification about deterrence and applications. Not comfortable words. I need you to say the truth. I need you to say, 'I built weapons that murdered civilians, and I knew what I was doing.'" Hartman's expression changed. The professional mask cracked. Something raw showed through. "Dr. Wells, say it. The situation was complicated. The war was... Say it." Her voice was harder now. "Say the truth without qualification. Say what you did. Acknowledge it. I need to hear you say it before you leave. I need to know that you understand, that somewhere inside, whatever you tell yourself to sleep at night, you know the truth." Hartman looked at her for a long moment. When he spoke, his voice was quiet, stripped of pretense. "Yes, I knew. We all knew. We told ourselves it was duty, service to nation, technical challenge. We told ourselves the Allies bombed our cities, so we were justified. We told ourselves many things. We lied. I built weapons to kill civilians, your brother, thousands of others. I did calculations to optimize range and accuracy. I tested prototypes. I solved problems that made the rockets work better, fly farther, kill more people more efficiently. I knew what they would be used for. I did it anyway. I am guilty of that. I cannot undo it, cannot justify it, can only acknowledge that I did it and I knew what I was doing." Tears were running down Wells's face now. Not sobs, just tears. Silent. "Thank you. That is all I needed. Not forgiveness, not friendship, not pretense that the past does not matter. Just honesty, just acknowledgement. You did terrible things. You know you did terrible things. That is enough. You may leave now." Hartman stood frozen for a moment, then nodded once, walked past her, down the corridor, out the door, gone. Wells stood in the corridor crying silently. Lubbock approached carefully. "Catherine." He said it. He admitted it. No philosophy, no justification, just truth. "I hated him for 4.5 years. Today, for 30 seconds, I saw him as human, as someone who did terrible things and knows it and carries it. That is worse than hating him. Hate is simple. This is complicated. Do you regret asking him? No. I needed to hear it, needed him to say it, needed to know that somewhere inside his rationalizations, he understood what he did. Now I know. Now he is gone. Now I can finish carrying what I have carried without him here. She wiped her face, composed herself. The work continues. We have rockets to build, British rockets, that use his knowledge but are not his weapons. That distinction matters. We carry his knowledge forward but not his guilt. Only he carries that, as he should. She returned to the materials laboratory, closed the door. Lubbock stood in the corridor alone, thinking. 4.5 years of work, of learning from people who murdered your countrymen, of professional cooperation despite moral horror, of necessity overriding principles, of building weapons to prevent war by threatening annihilation, of carrying impossible contradictions. Now it was over. The Germans were leaving. British engineers possessed the knowledge. The program would continue. The weapons would be built. The deterrence would be established. The moral questions would remain unanswered. That night Lubbock drove home, had dinner with his wife and daughter. His daughter was now 12. She asked about his work. He told her they completed an important project. She asked if he was happy. He thought about that question. I am relieved. I am satisfied that we accomplished what we set out to do. I am proud of the engineering. I am troubled by how we achieved it. All of those things are true simultaneously. That is what being adult in a complicated world means. Carrying multiple truths that do not resolve into simple answers. His daughter looked confused. His wife touched his hand. You did what you believed was necessary. You protected your country. You provided for your family. That is enough. Let the philosophers judge morality. You were an engineer. You built what was needed. Is that enough? It is what we have. Later, in his study, Lubbock wrote in his personal journal, something he had not done since before the war. He wrote, December 19th, 1952. The Germans departed today. The work is complete. Britain has rocket capability. We learned from people who used their genius for murder. Applied that knowledge to deterrence. Whether this was right, I do not know. I know it was necessary. I know we did the best we could with impossible choices. I know my daughter will grow up in a world where these weapons exist. I helped build that world. I live with that. Tomorrow the work continues. British rockets. British programs. Using knowledge gained from German expertise purchased with moral compromise. The technology progresses. The weapons improve. The moral questions remain. We carry them forward. That is legacy, not resolution, just carrying. That is what we do. He closed the journal, went to bed. Outside, cold December rain fell on Britain. Inside, engineers slept or did not sleep, carried knowledge or guilt or both, prepared for tomorrow, for next program, for next weapon, for next impossible choice that would need to be made in service of nation that needed protection in world that offered none. The turbopump that ran for 127 seconds sat in secured storage, ready for replication, ready for production, ready for deployment. Physical object that represented 4.5 years of work and moral compromise and technical achievement and human cost. It would be used to build missiles. Those missiles would never be fired in anger, would sit in silos and submarines, deterrent, threat, promise of annihilation that prevented annihilation. The logic was circular. The necessity was absolute. The morality was impossible. The engineering was excellent. All of it true. All of it the legacy. Welcome to 1952. Welcome to the world built on knowledge gained from people who nearly destroyed it. Welcome to the future where yesterday's enemies teach today's engineers to build tomorrow's weapons. Welcome to peace maintained by threat of destruction. Welcome to clarity purchased at cost of principle. Welcome to the age where we do what is necessary and live with what that means. The age we built, the age we inherited, the age we pass forward, the legacy.